Good evening, everyone. Welcome to Boise State's first Friday Astronomy. My name is Heidi Wu. I'm your host tonight. I am an assistant professor at Boise State Physics. And before we get started, I have a few announcements. And this is the last talk of the summer. And as you can see, we have a very exciting lineup for this fall. On September 1st, we will have our own Professor Brian Jackson telling us about the solar eclipse on October 14th. And in October, we will have Professor Yaoyuan Mao from Utah telling us about dark matter. And in November, we'll have Professor Alex Lapinko from Berkeley telling us about dark energy. And in December, we will have Professor Huang Laura from Yale University telling us about Titan. Should be very, very exciting. First Friday Astronomy are supported by audience members like you. We will appreciate it very, very much if you could consider donating to our events. And we have some code that you can scan for easy donation. And about today's talk, during the talk, so for people on YouTube, please use the chat feature and we will be monitoring the question and relate to speakers. And of course, if you are in here and you can just, at the end of the talk, I will ask you to raise your hands, ask your questions. Today, I'm very, very excited to be introducing Professor Bharat Ratra from Kansas State University. Professor Ratra is a Kansas State University Distinguished Professor in Physics. And Professor Ratra received his master's degree from Indian Institute of Technology in Delhi and PhD degree from Stanford University. He's one of the pioneers of this thing called dynamic dark energy, which sounds really cool. And I'm sure he will tell you all about it. And he's also pioneer in the density fluctuations in the early universe. If that sounds complicated, that's where we all come from, very, very early universe, all the way to today. And Professor Ratra has published so many groundbreaking works, and his papers have been referenced more than 20,000 times. That's an astronomical number. And he has also won so many awards. I won't bore you with all of those, but most recently, he was awarded the American Astronomical Society Fellow. And in addition to this great cosmology research, Dr. Ratra is also very active in outreach, and particularly in Kansas area and around the world. Tonight, I'm very, very excited to have Dr. Ratra telling us about, oh, sorry, I forgot your title. I'm very, very excited to have Professor Ratra give us a lecture about our universe. Please join me in welcoming Professor Bharat Ratra.
Thank you much for that really kind introduction. Can you hear me? Yes. Okay. Oh, okay. Okay. That's okay. Just click it. No. I don't see the green thing here. Okay. 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 No, no problem. Well, thank you very much for that really kind introduction. So I'm a cosmologist, and it's really great to be here. So I'm interested in the universe and stuff that happens on really, really large scales, and how those structures change in time, how they evolve. And this is a really great time to be interested in something like that, because we have great new telescopes, both in space and on the ground, with very sensitive detectors. And you've probably all seen pictures from the James Webb, and that's just one example. But there are many, many other telescopes. And these telescopes are collecting data that are reinforcing results or suggestions that have been around for a couple of decades. You've probably heard at least of the first one, and it's been in the news a lot. When we look out there and try to figure out the composition of the energy budget of the universe at the present time, we don't understand 95% of it. We know 5%, that's the atoms and molecules and the same kind of stuff we're made up of. But the remaining 95% is still basically unknown. We're seeing the gravitational effects of these things, and they've been given two names. One's dark energy and the other's dark matter. And it's really exciting that 95% of the stuff of the universe is unknown, basically. And that leaves us a lot of stuff to explore. The other result that's getting really strongly reinforced is that these cosmological observations are suggesting that either quantum mechanics or perhaps both quantum mechanics and relativity are incomplete descriptions of reality, and they need to be improved upon. And if this holds up, it's going to be really, really exciting, because quantum mechanics and relativity have been the foundations of physics for more than a century now. So I'm going to talk about cosmology, and I'm going to start with this picture. This is just 10 minutes away from where I live. These are bison. This is tall grass prairie. It used to be a ranch that the Nature Conservancy bought, and it's managed by our Division of Biology. And it's a really interesting place to go hiking. You can't go right through the bison herd here, but there's other areas where the bison aren't, and you can hike there. So I have a couple of questions, and you can answer them by putting your hands up. How many of you have gone hiking 10 kilometers in your life? What about 100 kilometers in your life? What about 1,000 kilometers in your life? Okay, I guess there's kind of an upper limit to the distances. I mean, you have a finite amount of time, and you can walk. And I mean, if you're really patient, maybe you can do 1,000 or 10,000 kilometers. The next question has to do with the smaller end of things. So I want those of you who have hair on your head to reach up and grab a strand of hair and feel it. And is that kind of the narrowest, smallest thing you can feel with your fingers, or are your fingers more sensitive than that? I mean, that's kind of the lower limit, right? So that's typical human hair is maybe 100 microns in diameter, 10 to the minus 4 of a meter. And if you have narrow, thinner hair, it's smaller than that. Maybe it could go down to 10 microns, a factor of 10 smaller. So we have a whole bunch of length scales here, and I'm using meters. So a meter is 3 feet, and a human scale is roughly around here. That's the typical size of a human. And if you have really sensitive fingers, you can get down to maybe 10 to the minus 4 meters. And if you're really patient and you can walk for a long time, maybe you'll get out to 10 to the 5 or 10 to the 6 meters. And this is kind of the range you're restricted in to probe directly with your hands and your feet and your senses. But there's a lot of structure on much, much smaller length scales and much, much larger length scales. And these are powers of 10. So you go from 1 to 10 to the 5, that's 100,000 times bigger, and then another 10 to the 5, and so on. And you cannot access these scales down here where you have atoms or viruses or molecules or quarks or leptons. You can't access them with your fingers. And you can't do the same thing over here. You can't start probing the galaxy using your senses. So the way we probe these length scales and these length scales is fundamentally different than the way we probe these length scales. And what we do on small length scales or large length scales, you take devices, so typically things like microscopes or telescopes or particle accelerators. And these days, we typically just collect light. So you can take a telescope and point it at a star and collect that light and then do things with that light. But you're going to store that as electronic signals on a computer. And the same thing happens down here. But on these scales, if you're really clever, maybe as smart as Newton, you can take balls and drop them and collide them, and you can watch falling apples, and you can figure things out like the conservation of energy and conservation of momentum and the inverse square law for gravity. But you can't do that on much, much larger scales and much, much smaller scales. You've got to build mathematical models and make predictions that you can compare to those electronic signals you store in your computer. So the way you build up intuition on human length scales, or we can call them Newtonian length scales, is fundamentally different than the way you build up intuition on much smaller length scales and much larger length scales. And so maybe it's not that surprising to find out that the laws that work over here and over here aren't exactly the same as the laws that work over here. And you get quantum mechanics that's really important on these length scales, and relativity that's really important on these length scales. And there's a sense in which that's kind of unintuitive, and it's unintuitive because you cannot access the large length scales directly the same way as you access Newtonian length scales and you build up Newtonian intuition. And so I want to spend some time kind of walking out from human length scales out to here, because a lot of times it's not really appreciated how much larger those length scales are. And there's two really nice videos. One's an old one by the Eames brothers called The Powers of 10. And if you search on Google, you can find that. And there's an American Museum of Natural History, update of that. I think it's also called The Powers of 10 or something like that. And they're pretty short. They're maybe 5 or 10 minutes long, and they're well worth watching if you have the time. So I'm going to start with this guy. And instead of a meter, I'm going to use an Einstein as my length unit. So an Einstein is roughly, 2 meters. And you can do this also in terms of his mass or in terms of his age, but we don't have time. So I'm just going to do this in terms of length scales. So I'm going to go from here to this picture over here, which has only been possible in the last 6 or so decades since we've had satellites in space with cameras. So that's Africa and that's Madagascar. And one way to think about this is to do an experiment, at least maybe a thought experiment, and we can drill a tunnel from the North Pole to the South Pole and leave a base here, and then go by 6.5 million Einsteins and put one at the South Pole and the next one on his shoulders and the next one on his shoulders. And eventually you'll cover the diameter of the Earth, and it would take you about 6.5 million Einsteins, so roughly 10 million Einsteins. So it's a factor of 10 going from our human scale to the scale of this small little planet. We can do this with the next big object in our solar system. This is the sun. And you can think about doing the same experiment, drilling a hole from the North Pole of the sun to the South Pole. And if you want to use the Earth as your measuring unit, you'd need to have 100 of them, one on top of the other. So the sun is a factor of 100 bigger in linear scale than the Earth. If you want to do this with Einsteins, you'd need 700 million Einsteins, almost 1 billion Einsteins. So this is roughly a factor of 1 billion compared to a human scale. And we can go out further. Oops, I don't know how to get rid of this, but I guess we'll ignore it for now. So that says the Earth-Sun distance, and maybe I should try to skip this. Is that it? Okay, great. Oh, was I not supposed to do that? Okay. Okay, so this is the next step we're taking. It's the Earth-Sun distance, and we know that the Earth goes around the Sun on approximately a circular orbit. It's slightly elliptical, but this is not to scale. And if we use our meter as the length unit, you have many, many powers of 10 over here. And if we think about this in terms of the size of the Sun, you need to pile up 100 suns in a row to reach from the Sun to the edge of the Earth's orbit around the Sun. So it's a factor of 100 bigger than the Sun. So we went from the Earth to the Sun, which is a factor of 100. From the Sun to the Earth's orbit around the Sun, it's another factor of 100. And over here, people introduce new length units. They don't use the meter anymore. It's not that convenient as a length unit. So astronomers sometimes use what's called the astronomical unit, and that's abbreviated the AU. And that's just the average radius of the Earth's orbit around the Sun averaged over a year. That's 1 AU. The other unit that's really useful is the speed of light, or making use of the speed of light. So light has perfected cruise control. Light in vacuum always travels at exactly the same speed. And it's a really huge number. We have it up here. It's 3 × 10⁸ meters per second. But maybe another way to think about it is that to cover a foot, light takes a billionth of a second. And you can see that pretty easily because a meter is 3 feet. So 3 × 3 is 9, which is approximately 10. So that's 10 to the 9, which is a billion feet per second. So in 1 second, it goes a billion feet. Or if you want to see how long it takes to cover a foot, it's a nanosecond, a billionth of a second. So we can, if we know the speed of light and we know it's all the same in the vacuum, no matter where it's going, then we can divide this distance by the speed of light. And if you divide that, you get 500 seconds. So we can say that the Earth is 500 seconds away from the Sun. And that's a way of classifying lengths also. So there's a very interesting point here. So when you're looking at the Sun, and if you look at the Sun, you should be really careful and use protective equipment. But when you're looking at the Sun, you're not seeing it in the present. You're seeing it 500 seconds ago in the past. And you're doing the same thing in this room. When you look at your friend next to you, if your friend's 2 feet away, you're seeing him or her 2 billionths of a second in the past. You're not seeing your friend in the present. But your brain doesn't really account for billionths of a seconds. And so you kind of naturally assume on human scales, you're seeing that person in the present, but that's not true. And it gets much, much more important when you get to very large scales because the time difference is much, much bigger. So we can take another step of this time it's 100,000, the factor of 100,000 from the size of the Earth's orbit to the next nearest star to the Earth, which is Proxima Centauri. It's part of the Alpha Centauri, the Centauri triplet system. And that's this many meters away from the Earth. But in terms of light travel time, when you're looking at Proxima Centauri, you're seeing it as it was 4 years ago in the past. You're not seeing it at the present. And in terms of AUs, it's roughly 200,000 AUs away from us. So people who study collections of stars, and those are not necessarily the same as people who study the solar system or collections of planets, they don't want to use the AU as the unit. Because you're starting to get many powers of 10 again. And so they use another unit called the parsec, which is abbreviated the PC. And that's a strange unit. This is a cartoon explanation of what a parsec is. So we take our observer and give her a telescope and ask her to go very, very far away from the Earth, so far away that this 1 AU here, this radius of the Earth's orbit around the Sun, subtends an angle of 1 arcsecond at her. And an arcsecond is a really, really tiny angle. So you go around a whole circle, that's 360 degrees. And each degree you can split up into 60 arc minutes. And each arc minute you can split up into 60 arc seconds. So an arcsecond is a really tiny angle. And so this has got to be a really large distance from the observer to the center of the sun if it's going to subtend just one arc second here, this one huge 1 AU subtends 1 arc second. And when it does that, the observer is said to be a parsec away. And this is also as an abbreviation. It stands for parallax of an arc second. That's where the name comes from. But for us, probably the most convenient thing is that it's roughly 3¼ light years. So when you're 1 parsec away, if you travel at the speed of light, it'll take you 3¼ years to reach where you're going, to cover that 1 parsec. And to put this into slightly more concrete terms, the furthest we sent humans is the moon, and the moon is roughly 1 1/3 of a second away from us. Excuse me. So Pluto, maybe which is Pluto's orbit could be kind of a characteristic size of the solar system. That's 40 AUs away, or 6 hours of travel at the speed of light. And if we look at Voyager, so these are the Voyager numbers from 2017, which was their 40th anniversary. They were launched in 1977. And Voyager 1 at that point had gone 140 AU, so roughly 19 1/3 hours of light travel time. But in terms of a parsec, it had barely gone even 1,000th of a parsec. A star, typical star, the closest star to us is roughly 1 parsec away. Voyager's gone maybe 1,000th of that distance in 40 years. So the distance between stars is pretty huge. So this one is Milky Way, and I'm sure if you guys have gone to the observing sessions here, yeah, this looks a little bit better. You've seen some of this. This is much better seen on your computer. It's called the ESO, European Southern Observatory Milky Way, and you can zoom in and look at it in more detail. But I'll go and show you an older one from Palomar, which was probably from the 50s or the 60s. So you can kind of see how much the imaging has improved. And for discussion, this artist's impression is probably a little bit better. So it's a disk. It's like a frisbee with a bulge in the center. And if you look at it from the top of the bottom, you can see this famous spiral arms. And maybe we should start with the size. The diameter of the disk is 50 kiloparsecs. So a kilo is 1,000, so it's 50,000 parsecs. And we know that 1 parsec is 3¼ light years. So we can multiply the 50,000 by 3¼ and we get 160,000 light years, or 160,000 years. And so if you could travel at the speed of light, it would take you 160,000 years to cross this. And you can't travel at the speed of light because you have mass. The only things that can travel at the speed of light are things that do not have mass. But it's a useful number, 160,000 years, and you can compare that to the 500 seconds to the sun, or the 4 years to Proxima Centauri. So there's a disk here. And this is a collection of maybe 200 billion stars. The stars are pretty heavy. The sun is sort of a typical star. Maybe the average star has a mass as half as large as that of the sun. So these stars are pulling on each other gravitationally. And so the moment you see an extended object like this that you know is being affected by a gravitational field created by all those massive stars, you know something else is going on, because if there wasn't something going on, all those stars would be pulled together at a point. And so what's keeping them extended in this disk is that they're systematically rotating in the disk, and they have energy of motion, and that's preventing them from all collapsing to a point. There's a bulge here, and the stars in the bulge are kind of moving around randomly. They have energy of motion also, and that's why they haven't collapsed to a point. And our galactic nucleus is over here, and that's where our black hole lives. It's not that massive a black hole. It's probably 4 million times the mass of the sun. And there's a lot of other galaxies whose black holes are maybe 1 billion times heavier than the sun. So the sun is about 1/3 of the way out. And you can see this band over here, this black band. And this black band is not indicating the absence of stars. What it's indicating is the presence of dust. There are as many stars in the black band as there are in the white patches above and below it. And what you're seeing here is the light that you're seeing with your eyes, that's being emitted by these stars in the black region. And they're scattering off the dust, or they're getting absorbed by the dust. And so they never make it to your eye. And so it looks black. And because this dust is absorbing this visible light, it's getting heated up. And it's got to start emitting something, otherwise it's going to explode. And it does emit light. It emits light at a longer wavelength or a lower pitch. It emits infrared light. And you've used infrared light if you've ever had muscle problems, kind of heat you up, heat your muscles up to cause them to relax. And so if you had infrared eyes and you looked at this wouldn't be a black band. It would be pretty bright and shiny. So our pictures of galaxies, they're all based on visible light. And if you look at galaxies using different kinds of light, they don't look like these spiral galaxies. They look very different. And you can go on to Google or Wikipedia or any reliable place and kind of Google for images of galaxies in different parts of the electromagnetic spectrum. And you can see pictures of the same galaxy in a whole bunch of different wavelengths. So there's the disk over here, there's the bulge and the nucleus, and all of this stuff is embedded in what's called a halo. It's kind of football shaped, and its diameter is probably a factor of 10 times bigger than the diameter of the disk of the galaxy. And we know this halo is there. We can see its mass, we can see its gravitational field. And it's where most of the dark matter lives around our galaxy. And embedded in this are these globular clusters, which are collections of hundreds of thousands to maybe 500,000 stars. They're really old and they're kind of spherically gathered together, and they orbit the center of our galaxy. They're actually orbiting inside the halo. And so that's kind of the characterization of our galaxy. It's pretty big compared to the solar system. But you can go and take another step outwards and, whoops, maybe I guess that's better. So this guy is our next nearest neighboring big galaxy. It's the Andromeda galaxy. And if you know where to look, and it's probably more prominent in the fall, you can look for this. And it's a really nice thing to look at. You see it at an angle, so you can see the spiral arms. You can also see the dust bands. And Andromeda is a little bit bigger than our galaxy. So it's about 60 kiloparsecs in diameter, maybe 200,000 years to cross it at the speed of light. And it's roughly 750 kiloparsecs away from us. And in terms of light travel time, that's about 2.5 million years. And that's kind of an interesting time. So when you're looking at Andromeda, so these electromagnetic waves, or the light waves, were created in a star on hot gas, and they traveled in a straight line for 2.5 million years, and they ended up hitting your retina and getting converted into an image of Andromeda in your brain. But they've been traveling for 2.5 million years. And if you go back and think about what was happening on Earth, then I guess the most famous hominin fossil is probably Lucy, and she lived in Ethiopia about 3.25 million years ago. And apparently, to escape predators, she used to climb up into trees, and she fell out of a tree 3.25 million years ago and killed herself by accident. But that's what was happening on Earth then. So this is Andromeda. We can go out even further. And galaxies, these collections of billions or hundreds of billions of stars, they kind of, if they come close to other galaxies, they're going to interact gravitationally and gather together, and they form what are called clusters of galaxies. And this is a nearby cluster. This is the Virgo cluster, and we're just looking at the central region of it. And every spot of light here you see is a galaxy. And each of them has maybe 100 billion or 200 billion or 300 billion stars. You can see some spiral galaxies and you can see elliptical galaxies. And the scale here is a few megaparsecs, a few million parsecs. So in terms of light travel time, if we call the few maybe 3 million parsecs, you can multiply that by 3.25. So it's going to be 10 million years to cross this at the speed of light. And this is the central region, and we can probably see about 2,000 galaxies here. So we can go out to an even larger scale and look at a patch of the universe. And this is, I'll go back to the picture of our galaxy. So we're here, and there's a dust band over here. And what we're going to look at is a patch up here, kind of a wedge, and well, you can kind of think of it as the distribution inside two spheres, one a smaller one and one a larger one. And we're just going to look at part of it over here. And that's, sorry, I'm going the wrong way. That's this picture. This is was taken at the Lick Observatory by Shane and Virtanen in the 1950s and 60s. And this was when they had, they didn't have CCD, so they had big glass plates. They'd put emulsion on it and stick it at the focus of a telescope. And they do this over and over again. And it shows you approximately 400,000 galaxies. This map was made later by Selner, Siebers, Groth, and Peebles. And these galaxy positions on the sky, I mean, these guys didn't have laser scanners, they didn't have computers. They sat there by hand and they figured out the position, the angular positions of 400,000 galaxies. And so those of you who are students here, if you have problems with your homework, you might think about this. So the scale here is 300 megaparsecs or so. And in terms of light travel time, it takes 1 billion years to cross this. These few pixels over here, this is the Coma cluster of galaxies. It's probably got 5,000 or 6,000 galaxies, each of typically maybe 200 billion stars. And that's just a few pixels over here. You can see other clusters of galaxies. And you can see two other structures if you look closely. There's dark regions. There's lots of dark regions. And there are one-dimensional filamentary structures. So maybe the way to think about this, so these regions are dark, not because there's dust on these scales. They're dark because there's no bright galaxies there. And they're called the voids. And maybe the way to think about this is bubbles in your bubble bath. When you're having a bath, the bright galaxies avoid the interior of the bubbles and they hang out on the surface of the bubbles. And that's why the voids are dark. And where two bubbles come together, you have a one-dimensional intersection and you have an enhancement in the number of bright galaxies. And that gives you the filaments. And where a whole bunch of bubbles come together, you can see the filaments kind of drain towards bright clusters of galaxies. You can see this filament goes over here. This one goes over here. This one goes to this one. This goes to that one. So a distribution like this is said to be very anisotropic. So we should start out with isotropic first. There's a bit of jargon here. When you're saying something is isotropic, you're looking around you in all directions, above you, below you, behind you, to your right and to your left, and it looks the same. And if you do that in this room, you don't see the same person on your right and above you. You see different things above you and below you and to your right and your left. And we can go out to a whole bunch of scales, but let's just go out to the surface of the Earth. And if you go a couple of hundred kilometers above where we are right now, you can see the Rockies in one direction. You can see the Sierras in another direction. You can see the Atlantic in one direction and the Pacific in another direction, and they all look different. Our solar system has a big star, and that's only in one direction. You look in any other direction, you don't see an equally big star. And our Milky Way is also anisotropic. And even on this scale, it's pretty anisotropic. You look over here, you see a void. You look over here, you see collections of thousands of galaxies. So maybe it's not that surprising. And the thing that might be a little bit more surprising is this one. So this is a picture that's on a scale, maybe a factor of 20 or 25 bigger than that previous one. And it's the afterglow of the Big Bang. So it was taken using the European Space Agency Planck satellite. That's a satellite that was sent up with microwave detectors on it. And if you've used a microwave oven at home, you know what microwaves are. They're pretty long wavelength electromagnetic radiation. And if you got a speeding ticket from a police officer, they probably used the microwave source. And they sent those microwave signals out from their microwave source. They bounced them off your car, and they collected them with a microwave detector. And because of the Doppler effect, they can figure out from the outgoing pitch and the incoming pitch how fast you were going. And so these are microwaves, and they had the satellite up here. So you can kind of think about being inside a big beach ball at the center and looking at the surface of that beach ball all over it from the interior and catching those electromagnetic microwave photons that were coming to you and figuring out the color by figuring out the spectrum. And once you know the spectrum, you can figure out the temperature. And so what I've done is I've sliced that beach ball from the North Pole to the South Pole and opened it out and spread it out over here. And if you want to reassemble it, you should take this side and try to join it up with this side and fold it up around you. So you can see that there's some red hot spots and some blue cold spots. And this detector managed to measure the temperature for all these photons. And so maybe the first thing you might be interested in is the average temperature across the whole sky. And that's about 3 degrees Kelvin. So the Kelvin is the temperature scale we use in physics. At 0 degrees Kelvin, all motion stops except for the Heisenberg uncertainty principle motion. And this room is roughly at about 300 Kelvin. So 3 Kelvin is very, very cold. And once we have the average temperature, we can then ask what the difference is between the blue cold spots and the red hot spots are. And that's roughly 30 millionth of a Kelvin. So the difference is 30 millionth of a Kelvin, and the average is 3. So if you want to take the difference, the delta T, and divide it by T, you're dividing 30 millionth by 3, and you get about 10 to the minus 5. Or if you turn that into a percent, it's 0.001%. So the temperature here and the temperature here are different only by a part in 100,000 or 0.001%. So it's very, very similar right across the whole surface of the sky on these scales. But when you go back down to these smaller scales, you can see it's much, much more bumpy. So these are 2 really important facts about the universe. One is that locally in our neighborhood on small scales, the distribution of matter and the distribution of light is bumpy in space. You look in different directions, it looks different. But when you get out to large scales, on the scales of tens of millions of light years, or even more than that, maybe hundreds of millions of light years, on average, the distribution of matter and radiation is isotropic in space. And I'm not going to go over this in detail anymore, but if you're interested, the way physicists understand these 2 facts about the universe is that it's based on what's known as the inflation model of the very early universe. And you can go and look on Wikipedia or Scientific American or Physics Today or Discover. As long as you go and look at reputable sites, you'll get a good description of what that is. And that's kind of an interesting thing. So let's move on to something that's even more bizarre, and that's that the universe expands. And if we want to understand this, we've got to kind of understand what we mean by it. So if you're saying something expands, that immediately implies you've got a measuring device that's not also expanding the same way. And so I've got my measuring device over here. And you can get a bigger one, a meter stick. And maybe it's kind of useful to understand why we think this is not expanding and we think that the universe is expanding. And so the useful thing to do is to try to understand what forces are holding this together. And on this scale, the relevant forces, there are two of them. So I have a little mass here. And if I don't support it, the big mass, that's the Earth, is going to pull it towards it. And it's also going to pull the Earth towards it. And we know what that law is. That's Newton's inverse square law of gravity. So if I have two masses over here, the force, the gravitational force between them is going to be proportional to each of their masses. And it's going to be inversely proportional to the square of the separation. So if I double the distance, the force goes down by a factor of 4. And if I triple the distance, it goes down by a factor of 9. So the other force that's relevant on this scale is the electromagnetic force or the electric force. And that's a little bit different than the gravitational force. The gravitational force is always attractive. They always want to come together. The electromagnetic force, there's two kinds of charges. There's electrons, which are called negative charges, and then there are protons, which are called positive charges. So if you bring two electrons together, they don't like each other and they're pushed apart by the electromagnetic force. And if you bring two protons together, they also don't like each other. They're pushed apart by the electromagnetic force. But if you bring a proton and an electron together, they're attracted to each other and they come together. So the electromagnetic force has a repulsive component and an attractive component. And it's again an inverse square law of force. So you double the distance, it goes down by a factor of 4. You triple the distance, it goes down by a factor of 9. And the name for that law is Coulomb's law. So we can do a computation if you have a calculator. So I'm going to have two protons and I'm going to bring them together. And gravity is going to want to pull them together and electromagnetism is going to want to push them apart. And the force laws of gravity and electromagnetism are the same. So it doesn't matter what distance they are apart from each other. The ratio of those two forces is independent of the separation. So we can figure out the ratio. And if we do that computation, we find that electromagnetism is going to push them apart by a factor of 36 powers of 10 stronger than gravity is going to pull them together. So electromagnetism is really, really strong compared to gravity. And I mean, we know that if we kind of think about our everyday experiences, so we're made up of atoms, and we have an atom has a positive charge at the center and an equal negative charge, a factor of 10 to the 4 further out. So atoms are basically empty space. And we're made up of atoms. The chairs are made up of atoms or molecules. And we're sitting empty space on empty space. So we should be able to fall through the chair or walk through walls because it's all empty space. And the reason that doesn't happen is because all these atoms are next to each other and the electrons don't like each other. So if you can kind of try to push them apart, they're not going to go anywhere, because the electrons in this atom is going to try to push apart from here, but it's going to be pushed from the other side by another atom. And it's this repulsion between electrons. The electrons don't like each other. That's what gives matter rigidity. And it's a really strong force. So I have a couple more questions for you. Are you pulling on your neighbor gravitationally? Okay, so are you pulling on your neighbor electrically? So who thinks you're pulling on your neighbor electrically? Put up your hands. 1, 2, 3, 4. Who thinks you're pushing on your neighbor electrically? 1, 2, 3, 4, 5. Okay, so there's about 40 people who didn't have an opinion. Are you guys just shy? So you're made up of atoms. And so you kind of think about what's happening. Your protons are pushing your friend's protons away, but your protons are pulling your friend's electrons towards you. And if you sit down and think about it, the push and pull get exactly canceled out because you're neutral. You're not electrically charged. I mean, maybe there's a few of you who biked in here or combed your hair really vigorously before you came in, right? So those guys might have some static charge built up, and then you're pulling or pushing your neighbor electromagnetically. But basically, when you get up to large scales, everything's neutral and electric force gets screened and it's no longer important. It's only important on scales like this, and it holds the meter stick together. But on large scales, even though gravity is so many powers of 10 weaker than the electric force, it completely dominates. And so when you want to do cosmology, you've got to use your most accurate model of gravity because you're talking about really, really large scales. And on those scales, the most accurate model of gravity we have is Einstein's model called general relativity. And Einstein, so Newton had a fixed space and he collided his balls in it, and there was uniform time, and he could see what these collisions did and bouncing things around. And Einstein realized that on large scales, or at speeds close to the speed of light, or in strong gravitational fields, it's a better description of reality to allow space to deform and time to deform in response to the experiment you're trying to do. So if you're going to collide two balls together, that space in which they live can deform in principle. And it doesn't happen until you start approaching the speed of light or really strong gravitational fields or really large scales. So we got to use Einstein's theory of general relativity. And we don't know how to really build up intuition on this because this only applies on really, really large length scales. And the way we build up intuition on Newtonian length scales is fundamentally different. So what we've got to do is we've got to write down the mathematical equations for Einstein's theory of general relativity and solve them and see what kind of phenomena they describe. And I'm going to do that, and then I'm going to translate that into English. And it's going to be a very inexact translation, but maybe it'll help a little bit. So I've got a one-dimensional space here. It's one-dimensional because you can choose an origin over here, and you can take your meter stick and walk along here, and you can mark off each point. And I'm going to get, I put a wave on it, an electromagnetic wave, and you can see it's a wave. It's got peaks and troughs. And if I had an extra pair of hands, so maybe I'll try to do it this way. I'm going to get the universe to expand, but because this meter stick is held together by the electric force, it's not going to expand, but the space there is going to expand. So it's expanding, and you can see that the wavelength gets bigger and bigger. So if you started out with something, in physics, blue light has a shorter wavelength than red light. So after a bit of time, this might turn red, the wave. And that's the expansion of the universe. Okay, so it doesn't happen that gravity goes to the end of space and starts pulling. That's not what's happening. What's happening is gravity is going into space. It's creating new space. The general theory of relativity creates new space. And that space has to go somewhere, and it spreads out. And everything lives in space. So as the space is spreading out, everything's taken along for the ride. And also, this doesn't happen just excuse me, in one dimension. It happens in all three dimensions. We live in a three-dimensional space. So there's a vertical axis here and two horizontal axes. So if you want to measure any point, you have to specify three numbers. So this is the expansion of space. And we can, oops. Okay, that's what I had up there. So cosmologists give this a slightly more mathematical formalism. And so you can kind of see my rubber band, my elastic band here at an earlier time and at a later time. And I've got an electromagnetic wave on it. It's got a wavelength. And as time goes on, the universe gets bigger. So by the universe, I mean the distance between my hands. And the wavelength gets bigger, and you can just draw this on an elastic band and take a meter stick, and you can measure this, and you'll see that it grows in proportion to the size of the universe. And so we want to have a way of defining something that characterizes the size of the universe, and very, very loosely, I'm going to call that the distance between my hands. And cosmologists call that the scale factor, and the symbol for that is A. and it's a function of time. So as time goes on, this distance gets bigger and bigger. And it's pretty easy to convince yourself by drawing on elastic exercise bands that the wavelength is going to grow in proportion to the scale factor. Astronomers don't like using the scale factor so much. They define what they call the redshift. That's the symbol for that is Z. And this is defined this way: as 1 plus Z is the value of the scale factor now at the time at which we live, at the time at which we're detecting the light, compared to the value of the scale factor at the time at which that light was emitted. So if we go and scale this up and emit the light at the same time as we're observing it, so we take t to be t now, this would be 1 and the redshift Z would be 0. But as we go back in time and go to smaller a's, then you have a smaller number in the denominator with a bigger number in the numerator. So this would be bigger than 1 and Z is bigger than 0. So Z increases as you go to the past, while the scale factor increases as you go to the future, and the time increases as you go to the future, and the wavelength increases as you go to the future. So this was the guy who first saw this red shifting, this change in color of the waves. And he did this in 1912. And if any of you have gone to Grand Canyon, you can see this. This is in Flagstaff, Arizona, at the Lowell Observatory. And you can see this telescope and you can see his chair and everything. So he pointed this telescope at a bunch of galaxies outside the Milky Way, collected the light, passed that light through diffraction gratings, broke it up into its spectrum, identified what atoms were causing that light, creating that light in that those external galaxies, and compared the wavelengths that he was seeing through the telescope with the wavelengths he could create in the lab. And he found all this stuff was redshifting. So no matter what direction he looked, it seemed as though things were moving away from him. So it's what happens when an ambulance goes past you. The pitch drops, the wavelength increases. And he didn't really know what he discovered. It took a little more work. Oops. Maybe I should be on here. No. I can't get this to move. Anybody have any suggestions? Okay, so okay. Sorry. Okay. Okay. Okay, so we're going to look at a three-dimensional universe, but before I do that, let's kind of think about what galaxies do. So the galaxies, after they're formed, they're like the ping pong balls, and they don't expand with the expansion of the universe. Their local gravitational field is strong enough to resist the Einstein space creation process. What's happening is the space between them expands, but the galaxies themselves, after they've formed, don't expand. But earlier on in the universe, when they're forming, things are more complex. And so what we have here is, so Slipher could have concluded that what he was seeing was that somebody in the past had set off this big explosion and was causing stuff to move away from him, a big firecracker at one point in space close to where he lived now. But that's not what's happening. It's something more interesting that's happening. So we're going to look at a three-dimensional universe here, three-dimensional space. So that's 1 dimension, 2 dimensions, 3 dimensions. And this is a cake with chocolate chips in it. And we're going to think about this a little bit, because if you go to the edge and look out, it's going to look different than if you look in. So if you want to have a three-dimensional flat universe, it can't be something finite. You've got to have it go out to infinity in all 3 dimensions, because if it had an edge, you looked out, it would look different than when you looked in. It wouldn't be isotropic. And I said on really large scales, the matter distribution, the light distribution is isotropic. So we're going to put down a bunch of galaxies. These are the chocolate chips, and we'll put observers on each one. And we'll ask the observer on galaxy 2 what she sees as the yeast rises. And she'll tell you every chocolate chip she can see is going to be moving away from her. And we can do the same thing with an observer on galaxy 6 and ask him what he sees. He'll say every chocolate chip is moving away from him. So the fact that Slipher was seeing all these galaxies move away from him didn't necessarily mean that he was at the center of the universe and everything was moving away. So a picture like this, where everything moves away from everything else, can also account for his observations. And that's the correct picture. So in this case, because we're expanding in 3 dimensions, then each of them has its own scale factor. And because it's isotropic, when you see what happens to the volume has to go with 3 parts of the scale factor. So it increases with 3 parts of the scale factor. So this uniform expansion is called Hubble's law. And this was discovered by Hubble, who was over here. He had a bigger telescope than Slipher, so he could see further out and he could resolve individual stars in these galaxies Slipher was looking at. And he realized that he could see some pulsating stars, and he identified them as Cepheid variable stars. And Polaris is a famous one, but that's in our galaxy. These are Cepheids in external galaxies. And Cepheids are extremely useful because of a discovery that Henrietta Leavitt made. So Henrietta Leavitt, that was probably in, I think, a few years before Slipher, maybe in 1905 or 6 or 7 or so. She worked at the Harvard-Smithsonian Observatory, which is in Cambridge, Massachusetts. And it's where astronomers would send their glass plates back to be stored. And astronomers, at least a few of them, tend to be a little bit obsessive. And so they look at the same region of the sky over and over again and take photographs of it. So Henrietta Leavitt had access to multiple photographs of the same region of the sky. And she realized she could see pulsating stars in these. So sometimes they would be bright and some other times they would be dim. And she identified them as Cepheid variable stars. And she could go to the nearest Cepheid variable stars and measure the distance using triangulation, which you do to measure distances. And if people aren't familiar with that, I'll talk about that later. And so she could measure the distances. And then she realized that because the pulsation period, that's something you can see even if you couldn't measure the distance of the star. She realized there's a relation between the pulsation period of these stars and the wattage of the star. So if you could measure the pulsation period, you'd immediately determine the wattage. And once you got the wattage, you can get the distance. So Hubble was able to measure the distance to these galaxies Slipher was looking at. And that's this R over here. And Slipher used Doppler's formula, the same formula that police use when they're giving you speeding tickets, to measure the speed. And this is Hubble's law. The speed at which these galaxies are moving away proportional to their distance from us. So a galaxy twice as far away is moving twice as fast. A galaxy 3 times as far away is moving 3 times as fast. And this constant of proportionality is called the Hubble constant. And it's got strange units because astronomers choose to use strange units, but we can see what its dimensions are. This is distance divided by time. This is distance. So the 2 distances cancel out and you have 1 over time. So the dimensions of the Hubble constant are inverse time. But because astronomers measure distances in megaparsecs and they measure speeds in kilometers per second, it has units of kilometers per second per megaparsec. And the number is not that important, but this is data that supports the Hubble law. This is taken with one of the main key projects in the Hubble Space Telescope that was led by Wendy Friedman. The Hubble Space Telescope, one of the reasons it was built was to measure distances and redshifts to galaxies that were much further away than had previously been done. And you can see this recession speed on this axis in kilometers a second, 10 to the 4, 2 times 10 to the 4, 3 times 10 to the 4. And the distances to these galaxies are on this axis in megaparsecs down here. So you go to a galaxy 100 megaparsecs away, it's moving away at about 7,000 kilometers a second. A galaxy 200 megaparsecs away is moving away at about 14,000 kilometers a second. And this red line is the Hubble law. The recession speed is proportional to the distance. So the larger the distance to the galaxy, the faster it's moving. And this is the expansion of the universe. I don't know whether I should continue or should I stop? Oh, five minutes, okay. So I'll just go through this really fast. And I pointed out that the data is spatially homogeneous on large scales, and that simplifies life a lot. Well, I told you that it's spatially isotropic. Sorry, so I should back away and explain what spatial homogeneity is. So when you're at one point looking around you in all directions, it's isotropic, it looks the same. But if you translate yourself to another galaxy and it also looks isotropic, there's a theorem in geometry that tells you that it's actually spatially homogeneous. And you're familiar with a really good example of spatial homogeneity. If you put on your scuba suit and swim around in a gallon jug of milk, it looks exactly the same white, no matter where you are, provided you don't get to the container edges. So there's much, much more symmetry. And that symmetry restricts the spatial geometries of the universe. So we can have a closed universe. So you're like an ant on the surface over here, and all you can do is walk on it. And maybe this is kind of where I should stop, and I'll do this demo over here about the expansion. And if people have questions, we can talk about dark energy and dark matter some more later. So what I've got here is an example of this two-dimensional universe. So you're an ant. All you can do is walk on the surface of this. There's nothing inside the balloon. There's nothing outside. And because the galaxies don't expand with the expansion of the universe, there are these little red patches that are stuck on. So if you're over here and you look at this neighboring galaxy, it can emit some light. Let's say it emits blue light. And that light doesn't take too long to get to you because it's close to you. And so maybe there's a little bit of expansion of space and it starts getting a purplish tinge. But if you look over here, that's further apart and it takes a little bit longer for that light to get here. So there's more space created and there's more of a purplish tinge. And then it gets even more purple. And over here, it can kind of get red. And you go from here to here, it takes much, much longer for the light to get here, and it starts looking red. So every point moves away from every other point, and the further away the galaxies are from you, the redder they look if they're all the same color, but they're not, and that's an additional complication. So maybe I'll just stop here. I'll be happy to answer any questions and talk about things that people want to hang around. Thank you. Okay, so the question is to try to summarize the difference between dark energy and dark matter. So I'll give you the difference between the two most popular models of dark energy and dark matter. So dark matter is probably composed of a bunch of particles, pretty heavy particles that are slowly moving. They're very slowly moving, and they're pulled together very effectively by gravity. on the scales of galaxies, even on the scales of the Earth and on the scales of the sun. While dark energy, if it's made up of particles, they're going to be extremely light, and they're going to be moving at speeds close to the speed of light, and gravity can only pull them together on scales of hundreds of millions of megaparsecs, hundreds of millions of light years. So dark matter tends to cluster on scales of galaxies and clusters of galaxies, while dark energy is kind of distributed pretty uniformly on those scales. That's kind of, oh, sorry. Can we detect particles of dark energy? I guess we can look at a particular model of dark energy and try to answer the question in that context. And it's probably going to be too difficult because dark energy is probably not going to interact with anything else at any realistic level of sensitivity that you're going to be able to detect it through a normal detector. So the main hopes are to see how its gravitational field affects things, because even though these particles are really light, there's a huge number of them, and collectively they make up maybe 3/4 or 70% of the mass of the universe at the current time. And so they have a really strong effect through their gravitational field, and they can affect how space is stretched and how it's contracted through Einstein's general relativity. And so that's the kind of test people are trying to do. They look at objects and try to see how far apart they are now compared to how far apart they would have been in the past. And that's what we use to detect the presence of dark energy now. Not on the Hubble constant, on Doppler's formula. Sorry, I should. Okay, so the question is, how does I mean, so the police officer or the Hubble law gives you the relation between velocity and the shift between the wavelength, incoming and outgoing wavelengths. And the question is, how does acceleration come into this? And maybe I should, well, I guess, do we have, I mean, do you guys want to hang around for another 5 or 10 minutes if people want to leave? Okay. Okay, so these are three different shapes. So you have the closed geometry, you have the open geometry, and the flat geometry. And maybe we'll just try to focus on the closed one. So what we have to look at is how this changes with time. And the easy way to think about this, yeah, for those of you who want to go, we can go ahead, and maybe I'll wait for a second if people want to leave. And we can kind of think of our dynamical variable as the radius of this sphere and get an equation for it. Oops, I have to get back. Where's, okay, I'm over here. Sorry. So that's our scale factor. It's the radius of the sphere. And as time goes on, it gets bigger and bigger, like you saw over there. And we want to get an equation for it. And so let's start with, there's a little bit of math here, so I'm going to apologize for that. And if you have questions, just go ahead and ask me and I'll go over it again. So the dot means the rate of change of something. So when you say something dot with over dot on it, that's the speed. So because A is the displacement, A is the radius. So we know that the Hubble constant, or the Hubble constant at earlier times, it's a function of time. That's the expansion rate. It's the rate of change of the scale factor divided by the scale factor. And the question was whether this is increasing or decreasing with time. So we know it's positive because everything's moving away from us. It's redshifted. And so we want to know whether the person driving the expansion of the universe, whether she has a foot on the gas pedal or the brake. So we know it's the expansion has started. So she started moving. Then if she has her foot on the gas pedal, she's going to start moving faster and faster. If she has a foot on the brake, she starts moving and then she slows down and then she eventually stops. And there's a kind of complicated equation over here. And I'll try to describe this in words. And this is the acceleration. 2 dots is the rate of change of the rate of change of something. So it's the acceleration. And this equation is very, very close in form to the famous A equal to F over M equation, or maybe people remember it more as F equal to ma equation, Newton's second law of motion. Is that kind of familiar to some people? Okay, so there's an acceleration, which unfortunately is called A, and there's the scale factor, which I'm calling A, and it's very, very unfortunate that the conventions in these 2 separate areas of physics use A for different things. So whenever I write down an acceleration here, I'm going to have 2 dots on top of it. So this is A equal to F divided by M. So it's just another way of writing Newton's second law of motion. The G is Newton's big G. It's the gravitational field that's causing the acceleration, and that's the strength of the gravitational field. You can forget the 4 and the pi and the 3. They're kind of irrelevant for this argument. So what we're doing is we're looking at this expanding balloon. And I told you that we could have a flat universe that was infinite. And if you have a flat universe that's infinite, it's got an infinite amount of mass. This is more compact, it's finite, and it doesn't have an infinite amount of mass. But because we've also got to discuss universes that are infinite and have an infinite amount of mass, it's not convenient talking about the mass of the whole universe. So what we're going to do is we're going to look at the expansion just over here and look at the amount of mass in these galaxies just over here and talk about a mass per unit area or a mass per unit volume. And that's what I have up over here. It's the symbol rho sub m, which is the mass per unit volume. So you take a little chunk of space, you add up the mass of all the galaxies, you add up the mass of all the dark matter, you add up the mass, I'll put dark energy somewhere else. I'll just do the galaxies and the dark matter. And that's the mass per unit volume. So let's just forget all of this stuff over here. So there's a minus sign over here, and this tells you that the acceleration is minus times the mass density. So let's go back over here and kind of think about what this is telling us. So there's 2 things going on over here. Newton would tell you that these 2 guys are going to pull on each other because they're 2 massive objects and they have a gravitational field and they pull on each other. And Einstein is going to want to come along and create space between them and push them apart. So if you have a lot of mass, Newton's going to win over Einstein. If you don't have that much mass, Einstein's space creation process is going to win. But this is just with normal matter. So we can look at what this tells us. This tells us that if you have just mass over here, you're going to get deceleration because of the minus sign. She's got her foot on the brake. Now, these galaxies, I mean, this is also not a really great demonstration because Newton's going to tell you this galaxy is going to pull this galaxy towards it, and they're going to start moving across the surface of the balloon. And I haven't figured out how to demonstrate that on this balloon, but they're going to move and they're going to come together. And you know what motion is. I mean, if you kind of think about pumping air into a tire, you're pumping air molecules in there and they're bumping into each other and they're giving you kind of a pressure. So pressure is a characteristic of energy of motion. And that's why I've added this guy over here. Where have I gone? I've gone over here. That's why I've added a term P over here. That's the pressure caused by the energy of motion. And because motion is in 3 dimensions, there's a 3 over here. So for those of you who know a little bit of general relativity, this combination, the mass density plus 3 times the pressure, is called the active gravitational mass density. And if I was not using units in which the speed of light was 1, I would have to put the speed of light in the denominator of this term and square it. And so that immediately tells you this is a relativistic effect, and you only see this on really large scales for, that's important for general relativity. So even when you have the galaxies moving, this is still a positive quantity. And so you're going to predict there's a deceleration. So you go and tell your astronomer friends to go measure this, and they come back and tell you in 1997 and 1998 that actually they're measuring an acceleration. So then you're kind of stuck. You can either say Einstein was wrong and this equation is irrelevant, so we don't have an inconsistency, or if you're a little bit more conservative and realize that this generalizations of this equation describe black holes extremely accurately, they describe gravitational waves extremely accurately, they describe the cosmic microwave background pretty accurately, then you want to try to preserve this equation, you want to try to preserve general relativity. And so then you come in and introduce a hypothetical substance, which you call a cosmological constant, and that's the symbol lambda, and it has a mass density and it has a pressure. And you choose it to have a very strange equation of state that the pressure is equal to minus the energy density. So the stuff in this, in these round parentheses over here, if you replace the pressure with minus the energy density, then you have rho lambda plus minus 3 rho lambda. So rho lambda minus 3 rho lambda gives you minus 2 rho lambda. So this is a negative number. And then you make its magnitude big enough to totally overwhelm this guy. Then everything in the square parentheses is negative, and that negative cancels that negative, and you get an acceleration. And then you tell your observer friends you can get a positive acceleration by introducing a hypothetical substance called dark energy that has this strange equation of state. And it's not that strange because we see substances like this in the lab. They have complex names, this phenomena. So you could go search on Google and look for the Casimir effect. And maybe Wikipedia has nice introductory descriptions, or look for something that's a little bit more introductory, or the Lamb shift in the hydrogen atom. And these have to do with the uncertainty principle and 0-point fluctuations in quantum mechanics. And they behave the way we want a cosmological constant to behave on cosmological length scales. We've seen this behavior in the lab. We haven't seen this behavior on cosmological scales, and we don't know whether we're going to see it or not. But if we model it on what we've seen in the lab and introduce this into general relativity, then it can explain the accelerated expansion. And I can tell you more about how this expansion was measured, but okay.
The people have questions to come over and the video, and let's thank again.
Thank you. So I guess I should shut this off.